So, I guess to start, this is going smoothly here at the beginning. Um, here is my plan. Uh, my plan is that I'm old and tired, and I there you go. I kind of want to just be done. So my plan is we're gonna finish out this week. I'm gonna go through some stuff today. We'll see how far we get. I'll try to look up some examples today and tomorrow, and then we can do some examples on Thursday. And then my hope is to have your exam posted either Sunday night or Monday morning, and just give you all next week to work on it, and then not have class, and for you to use that class time to either exam or work on your project that you should have already been working on, uh, and just call it good. So we'll finish lecture up this week, and then if you're anything like me, you need a break. So I think we'll just call it after Thursday, and we'll see where we get. Hopefully, you learn some stuff along the way. I don't know. It's not about the chemistry; it's about the friends we make along the way, or something. And then we'll be good. So, like again, for the lab, for everyone in lab, we've got lab uh, Wednesday and Thursday, and that'll be done as well. So basically, other than like your exam project and some final I have to like whip up, you'll be done after Thursday, after this week. So, with that, no one's arguing, so this is good. No one's like, actually, I wanted more of this. Um, so let's look at, let's say we have something that looks like this. Right, we wanted to add, I don't know. Yep. Right. So we wanted to do that. We wanted to model how it would add, right? We wanted to predict the stereochemistry. We could use the CRAM model because that's the one we know. Right. So how would we do that? What would we need to do the CRAM? So it's not the CRAM chelate because there's no group that can coordinate a metal. So you have to draw that weird like Newman projection-esque thing where you'd have your carbonyl, in this case an aldehyde would be at the front. It's a really ugly circle. Slightly better. And then we would have to put our groups around that Newman projection with the large group, which in this case should be the phenyl, would be straight down if we were using the CRAM model. And then we would have to have our medium group and our small group. So I think should be medium and small. Right? Now what you want to check, right, is the whole point of this is you want to make sure you're predicting the right R and S for the alcohol that you make. So you need to make sure that the R and S of our of the chiral center that I just drew is right. So we should probably check. So this would be 1, 2, 3. Carbon makes, or methyl makes 4. So this looks like it's R, right? But the low priority group points at me, so it's S. All right, so now I need to make sure that the thing that I just drew is also S, right? So this would be 1, phenyl would be 2, ethyl would be 3, and 4. Now, what I can do, and hopefully, I don't know if you guys can do it, right, is I kind of look at it as we're looking at the molecule like this, where this is the hydrogen and it's pointing back, right? Not the hydrogen, sorry, the methyl group. This is the 4. So in my head, I'm just turning it like this. So I guess I should turn it away from you, like this. So the low priority group points away from me, and that puts the aldehyde on the left, then the phenyls at the bottom, and then the ethyl is like this. So like I'm kind of in my head making it look like this. Like that. So I'm just kind of turning it. So I'm kind of almost like grabbing the phenyl and spinning the molecule by the phenyl, by that bottom bond, so that I can get it in an orientation where I can go 1, 2, 3, and have my low priority group pointing away from me. And then that is S. So I know now that I had S in my starting molecule, and I've drawn my model with the same stereochemistry. So now my nucleophile, which is the ethyl, right? It needs to add to the molecule from the side of the small group, because that's the group that's easiest to get past. So when it adds over there, pushes electrons up, it kind of pushes the oxygen over, or what the model we have drawn looks like it does, right? Is it says, okay, I'm going to go over so I can actually draw this and have space. I'm sorry, don't hate me. I'm going to come back. Right, so I've got phenyl, methyl, ethyl group added here. Right, so you have, so the way they did it, the way I have it in the slides is I leave the oxygen where it is. The ethyl group stays on the side that it approached from, and the hydrogen kind of gets pushed over. So you keep it in that staggered conformation. You don't get it to eclipse. You just leave it like this. Now, I can look at this and say, okay, again, the group that is, so I'm setting the stereochemistry for this carbon, the one I just made. So that's 1. The group that's back, the one that's hard to see, is 2, 3, and 4. So kind of the same thing that I did before, right? Where now I've got to kind of turn it so that I can see everything. So now you can kind of imagine twisting it by the OH, and that's going to leave your oxygen in the same spot. Your 1's going to be in the same spot. OH. But I've got to turn it so that hydrogen, that low priority group, is back away from me. So that's going to put the group that is 2 over here, the group that is 3 over here, and then the hydrogen ends up back being 4. Everyone kind of see that, where I'm just kind of turning it, and I basically turn it like, was that like a third of a turn? Now I can assign 1, 2, 3. This is S. So when I go to draw my product, I should have the S stereocenter for my alcohol. So I come back over here, right? The stereocenter that I started with doesn't change at all, right? Because I didn't do anything to those carbons. And then I have O and the ethyl, and I've got to set it like, I got to say, okay, if this is 1, 2, 3, right? Where do I need my hydrogen to be? My hydrogen needs to be back, right? Because the way that's numbered is S. So I'm going to put wedge, hydrogen is on a dash, and then this is S. So you just got to make sure that you get from your perspective drawing to the right stereochemistry in your model. And then once you've used your model to get your stereochemistry of your alcohol, you need to be able to go back to your perspective drawing to be able to draw it out. So it's just doing a lot of R and S stuff. And I think the hard part is just in your head being able to like see and like turn the models so that you can get to a confirmation that you can do R and S with. Because you could have done, right, for this, you could have also thought of it as if you were like on the side looking at it, where you're like, oh, so instead of looking at it straight on, you can think, well, if I look at it from the side, it's aldehyde, phenyl, ethyl. I'm going counterclockwise, so that's S. Or you could do what I drew, which is just kind of turning it and getting that hydrogen back. Whatever works, but you need to be able to get it in the right orientation. And then what if we had so here, since I'm using a metal like magnesium, and I have a group with lone pairs at the alpha carbon, I can use the cram chelate. Oh, forgot an H. Cram chelate model, where the magnesium is going to get bound between the carbonyl and the nitrogen. Right. So what's probably easiest to do is to put your carbonyl and your group that coordinates it in the same plane. So now you can see I've got my magnesium. Phenyl is forward, methyl is back. So basically all I did is I just kind of pushed the nitrogen back. And so that when this bond rotated right here, that nitrogen getting pushed back pushes that phenyl group to the forward position. And again, you can always go 1, 2, 3, 4. This is R, and then 1, 2, 3, 4. This is still R, right? So I didn't change anything. I just kind of rotated that single bond a little bit. And in doing that, now you clearly have the phenyl group is forward, the methyl group is back. Phenyl is bigger than methyl. So your nucleophile is going to come from the same side as the methyl group. So you're going to add, so when you're done, you're going to end up with, if your nucleophile comes from the back, it's going to push your oxygen forward, and then you can have your, oops, ugly. And then you're going to have something like that. So you can use your model to kind of predict what you're going to end up with. So what I want more examples of is like cram things to get the exact like what salts you have to use, because you can use different reagents and then add salts to, like, you can add a lithium like perchlorate, and then you just get the lithium to coordinate, and then you can use another nucleophile. So I want to get some examples of that. I just didn't have time. Organic 1 exams on Friday, man. I can only torture so many people. So, and I wasn't gonna come into work on Friday. I was just gonna stay home and work on your exam. I have to do a 2.5 hour meeting on how to order stuff. Yeah, so I just want to like jam a pencil into my head because I was like, oh, I'll just spend all day making their exam on Friday. No, I've got to sit through 2.5 hours of like how to do online shopping in the university space. And I'm just like, I've been using Amazon for years. I have this down. My bank account knows I can shop online. Okay. Oh, does anyone know if Katie Hunt's okay? Because like she hasn't shown up to the last two classes, I don't think. Okay, maybe she's watching videos. I should email her because like last week I was like, but now it's 2 days in a row. I'm concerned. Is she in here and I'm just missing her? Oh, Caitlin Hunt, yes. Okay. Okay, as long as she's alive, like I'll email her and make sure she's okay. All right. So another model that was developed to explain additions to carbonyls is the Cornforth model. And so here you have your carbonyl and then whatever small. So your G group is an electron withdrawing group. And so you put it on the opposite side from the carbonyl. So, right, if you think about if G is electron withdrawing, right, you're going to have a dipole that points towards G, right? In your carbonyl, the oxygen is electron withdrawing, so you have a dipole that points towards the oxygen. So if you put them on opposite sides, you minimize the dipole in the molecule, right? Because they're pulling in opposite directions and they cancel each other out, right? So if you have a situation where you could use the Cram chelate model, but you don't have one of the metals that lets you chelate, you can use the Cornforth model to explain it, right? And then this does kind of the same thing, where now your nucleophile is going to approach from the more open face, which is the side of the small thing. So when you add your nucleophile, right, it's going to be on the same side as the small group. So it's going to push your oxygen back, leave our R group in plane. We're going to put our nucleophile on the front. Right. So if you have, like I said, if you don't have the right metals, so if you don't have for the chelate, right, you need a hydrogen or you need lithium, magnesium, tin, uh, titanium. There it goes, like wrong thing, and aluminum. So you don't have one of those metals to bind that electron withdrawing group, usually an oxygen and nitrogen, to the carbonyl. It's going to try to arrange itself in this way. Yeah, so if you have, so let's say you had, right, so you had this, this is kind of a stock example or something similar to it, right, and then big group, right, clearly big group, right? If you had, let's say, this, and so you had like tin chloride, right? The tin's job is going to be to grab the two oxygens, right, and hold it in that chelated shape, right? Cl4, whatever. Right, so that's the tin's job. So now we've made our chelate model, and we're going to add from the open face. We're going to add from the side of the small thing, and we're going to get our product, where then this is going to be back, and then our ethyl group's going to be forward, right? But if I'm do something where, let's say I have the same thing, right? But let's say you have, I'm trying to think of a good reagent here. So you have like a boron. These boron reagents can allylate. They can just like transfer an allyl group. The boron can't make that chelate, right? So now you're going to say, all right, let me minimize my dipoles because I can't use the boron to grab the two oxygens. So now you're going to say, all right, it's going to react kind of like this, where now I have to flip this over. So now tert-butyl is forward and methyl is back. Now you're going to come from the opposite face. And then that's going to have you end up with your allyl group being back and your oxygen being forward, because it changes what the open face is. So this is why I want to get some better examples, just so I can make sure I give you the best info. But if you don't have something that's going to grab those two oxygens, now you want to minimize your dipoles and have it add that way. Make sense? Okay. So, right. So over here, this way, right? So this is where the chelate is lithium, hydrogen, magnesium, titanium, tin, and what was the other one? I just said it, aluminum, right? So you're going to do the chelate when you have one of these metals present. So either as part of your reagent or as like an additive, where like lithium holds okay, but you can add a more chelating metal that's going to really hold that ring together. So you can add a titanium, or you can add magnesium to make that work. Where if you have something where with boron that's not going to make that chelate, then you use this other model. So these models that we've talked about, the CRAM model and the Cornforth model, were developed kind of early on, and then there was kind of a grand unifying, if you will, model that it's kind of explained all the different observations of how these worked, and that's the Falcon-On model. Right, the CRAM and Cornforth models work. Like that's not the issue. But the Falcon-On model does a better job of kind of explaining all the data that you see and all the observations. I will say in the slides as well, so if you can make the chelate, if you can do one of those chelate models, you're going to prefer to do that. Like the CRAM chelate model wins over the Falcon-On model. right? But the Falcon-On is kind of the better explanation of the Cornforth and CRAM models, but CRAM chelate wins, right? And part of how we came to this was that this is based on calculations. And when we were making these models initially, it was we run the experiment, we see what we get, then we kind of work backwards. This was we take all the data, we calculate what the lowest energy conformation of our carbonyl is when it reacts, and that better explained all the observations, right? So as I mentioned before, you have your carbonyl, right? Whatever your groups are, we're not going to worry about that right now. Well, kind of worry about it. Ah. Right, so you've got your groups, and your nucleophile has to approach at this angle. It is 107 degrees from the kind of the carbonyl, and this angle is the Bürgi-Dunitz angle. So what's happening is I want to use this term just a little bit, right? So there are two things we have to think about when things react. We have what's called a HOMO, which is the molecular orbital that has electrons in it. It's the highest occupied molecular orbital. So it is the molecular orbital that's at the highest energy that actually has electrons in it. And then there's the LUMO, which is the lowest, unoccupied, I'm not going to have space, molecular orbital. And that is the empty orbital in a molecule that is at the lowest energy. And these two orbitals are what react in reactions. Is you have this orbital that is full of electrons that can give electrons to something, and then you have this empty orbital that can accept them. And so what happens is you've got your HOMO, your HOMO, and then that empty orbital, the LUMO, they're close in energy. Right? So they're close enough that they can react. If you get a big difference between the HOMO and the LUMO, they can't react. The energies are too different. But if your energies are close in your HOMO and your LUMO, you're going to get a reaction to happen. So that the Bürgi-Dunitz angle allows your nucleophile to approach the LUMO of the carbon-oxygen double bond, right? That is the pi star orbital. So starred orbitals, so when you ever see so if you see pi star or sigma star, the star means that's the anti-bonding orbital. So when you put your electrons into that antibonding orbital, you break a bond. So adding electrons to an antibonding orbital, as you're making a bond, you're breaking another bond. So, right, kind of the example that you guys all know but don't realize you know is, remember SN2 reactions, right? So when you had your carbon, I know everything's blue today. You had your carbon, not a copper, dear God, carbon, and you have your leaving group. You always approach the carbon from the opposite side from the leaving group. The reason is there's this little antibonding orbital right back here. So your nucleophile puts electrons into that antibonding orbital, right? And by filling that antibonding orbital, it breaks the carbon leaving group bond, right? So it turns that antibonding orbital into a bonding orbital. It goes, hey, I'm going to give you electrons. You have to break your leaving group bond, your bond to the leaving group, and now now that orbital is going to be a bonding orbital for me to bond with the carbon. So as you fill that orbital, you break one bond, and it allows you to make the new bond that you're making, right? So the Bürgi-Dunitz angle, that's where the antibonding orbital, that's where that orbital that you have to stick your electrons in is. So your nucleophile has to come, God, that got really bad, has to come along that 107-degree angle to fill that orbital. So every time a nucleophile comes and adds to a carbonyl, it comes along the same trajectory. It comes along that same path, right? So kind of based on that, what they were able to propose is what I've been drawing, where the Falcon-On model is you have your carbonyl, right? You have some group G, right? Where it's just group. And then you have your large group and your small group. And your nucleophile approaches along the Bürgi-Dunitz angle, and it goes over the small group, because that is the easiest group for the nucleophile to get past. So it approaches, and so it always goes over that small group to get to the antibonding orbital. So G is the group that most wants to be sure I spell this right. So orthogonal is a word that I don't use in my everyday life. So this is the group that most wants to be orthogonal or perpendicular to the carbonyl, right? So these groups are large groups or electron withdrawing groups. So if you're a big alkyl group, you want to be perpendicular to the carbonyl. If you are an electron withdrawing group, you want to be perpendicular to the carbonyl. So, right, this model, let's say we have, I should give you the list of G's first. All right, So methoxys, or just kind of general ethers, right? So if you have a methoxy group, these most want to be orthogonal, right? Then the next thing are large alkyl groups like, oops, no, like tert-butyl, right? Then you have phenyl, then isopropyl, then ethyl, methyl, H. So you've got the things that electronically want to be orthogonal, right? And then it's kind of decreasing size, right? Tert-butyl, phenyl's kind of weird. Phenyl's part electronic, part size. And then isopropyl, ethyl, methyl, hydrogen, right? After phenyl, it's clearly just as they get smaller, they less want to be perpendicular to the carbonyl group. Right? So as you get smaller, you less and less want to be orthogonal. So what you can do is, right, so you have again, I got to think of something here. Right, so okay, we'll use this generic boron reagent. Right. Right, we're not going to chelate. We're going to use the Falconon model. That's going to give us our carbonyl. Right. And again, the hard part is making sure that we know where the methoxy is going to go. We know it's going to go perpendicular to the carbonyl, but we need to make sure that we put it on the right side. So again, we need to do 1, 2, 3. Oh no, the dreaded in the plane for number 4. So we can redraw it, right? Do the trick where we just switch whatever group is back with 4. So now we've got 1, 2, 3. This is 4. So this is S, which means what we started with is R, right? Because when you switch the two groups, when you like switch the 4 with the group that is back, you make the enantiomer. So we made it easier to figure out this to being S, so we know that this had to be R. So now we have to make sure that we end up with R on our model. So I kind of see it, so let's go that, this, and this, and we can check me. All right, so kind of 1, oops, nope. Oh, did I do that backwards? I did that totally backwards, it's fine. I messed up our stereo center. Right, these should switch, but yeah, it's all right. It's all right. It's only totally backwards. But, so fun fact, I'm fixing this because then when you look back on your notes and be like, what a dummy. But the trick is, right, we're only trying to make sure that the stereo centers are the same, right? We're not having to report out R and S exactly. So if you, for some reason, like I just did, screw up your priorities, as long as they're the same, as long as you screw them up the same way, on both, on the chiral center that you're determining and the one that you're drawing in your model, you're going to end up with the right answer, right? Because you're going to get all the groups in the right place, right? But I should, do it right, whatever. So let's check here. 1, 2, 3, right? So if that should be S, so again, we can do this a couple different ways. We could try to rotate it, right? So that it would be, I think the way I'm doing it right now is I'm kind of looking down, saying, hey, if I'm looking down and put that methyl group behind me, I go 1, 2, 3. That's counterclockwise. That's S. We could also try to, like I said, we could try to do what we did before, which is like turn it. And so we'd have to spin it around a little bit. And I think we end up with, it's so hard. Oh, kind of see it. So you could end up with like O down here, this up here, this over here, and that methyl group kind of back. And that is also S. All right. So now it's going to look like this. And now I've got to add my nucleophile along the small group. Right, and this is going to do the same thing basically that we did before. We're going to basically put our nucleophile in the spot between the large and the small group. So we're going to end up with OH here, H here, methoxy, isopropyl, this guy, and then poorly drawn our nucleophile right there. Right, so you're adding your nucleophile between the two groups and then pushing the oxygen and the nitrogen and the hydrogen over into like the open spaces to end up with a staggered Newman projection. So we know that this part stays the same. Right, we got to figure out where our oxygen, and in this case our nucleophile, is this allyl group. Right. So if we come down here, right, we've got to assign RNS to this chiral center right here. So we're going to say, our oxygen is 1, right? The group that is back, right, that we can't see, that group would be 2. The nucleophile would be 3, and the hydrogen would be 4. Again, I think the easiest thing to do is to kind of think about looking at it straight down, where you'd go 1, back to 2, and then 3. So if you're looking down on that clock, you're going counterclockwise again, and that puts the low party group away from you. So counterclockwise would be S, so we need to end up with S again. So if we went 1, 2, 3, hydrogen would need to be back, so that would put our oxygen forward. Seem reasonable? So what if we had again, like right from the jump, you know what the product is, you just don't know the stereochemistry, right? You're like, oh, I 100% know this is my product. Now I just need to Now I just need to figure out R and S, right? So again, this will do it right. 1, 2, 3, and of course I put the low priority group there. Way to go, me. We'll switch 4 and 2. 1, 2, 3, 4. So this would be R, so this is S. So then when we draw our model, right, we know our tert-butyl group is going to be orthogonal. We just have to make sure that it's the right stereochemistry. So, right, if we did it this way, hopefully it's not the exact same thing. I tried to make it different. We'll see. Right, if it was this and we went 1, 2, 3, this is 4. Right, if we look down on it, that looks like it's clockwise, right? Right, if we're going aldehyde, tert-butyl, ethyl, clockwise, that's R. So that's not the right stereocenter, right? So we've got to make it the correct stereocenter, which would require me to go right, 3, 4, right? If you switch two groups, you make the correct stereocenter. You make the enantiomer. So I made the enantiomer, so this should be S, but now it's not arranged properly, right? I need to have my small group at the bottom so the nucleophile can go over the smallest group. So that means I have to rotate this whole thing around to put the tert-butyl group orthogonal, but on the other side. So if I rotate that, I'm going to pretend I have an iPad Pro and have a big screen. We're going to go to another slide real quick. Boop. If we rotate that, so we had this. We need to have this small group, so it's along that Bürgi-Dunnes angle. So we're going to just kind of rotate the whole thing. Right, so this is just like when we rotate this stuff for Newman projections. We're just going to spin all the way around. Tert-butyl, ethyl. Now methyl is towards the bottom, right? That small group's at the bottom. So then we can run our nucleophile, right, which in this case is ethyl. Right, we can run our nucleophile, which is an ethyl. We'll make it ethyl. Right along there. So we're going to stick our nucleophile between the small and the large group. When we have our Newman projection, it's going to be there. There. OH here, hydrogen here, tert-butyl there. Right, so you're going to stick that nucleophile between the two groups, basically on the opposite side, like anti to the G group, to the big group that you put perpendicular. Now, 1, 2, 3. Again, if I look down, that's going to be counterclockwise. So that should be S. So let's check over here. How do we have to arrange this? 1, 2, 3. This should be S. Right, hydrogen back. So if like on an exam, I was like using the Falcon-On model, predict what your stereochemistry is going to be, I would want you to draw the model, right? Basically this guy, with the right stereochemistry on the group in the back, and then draw the product, and then get from that stereochemistry of this carbon, get it translated to there. Right, so I could give you something like this exact problem basically, and say, hey, what's the product of this with correct stereochemistry? Use the Falcon-On model to explain it, and you would need to draw me some circles. So that's what I would be asking for, something like that, is where you can like predict what you're going to do. So some actual examples. Let's see if I can get these to work. And this one's just kind of neat, so because it does two things. Slide. There you go. So I kind of drew what the model would look like down in the bottom. So they're using diethyl aluminum. They're using slide. So this right here is their nucleophile. So kind of like my generic boron reagent. A lot of times when you have a metal at the allylic position, it's able to take its electrons and push down and push these electrons out to go add to something. So in this case, it'll add to an aldehyde. Even though it's an aluminum, the chiral center isn't this methoxy group isn't alpha to the carbonyl, so it doesn't do the chelate model. So it's doing the Falcon-On, and so you have the chiral center right here, translated here, and your small group's the hydrogen. So it's going to be arranged like this, where you're going to approach it from this side, and it's going to give this product. What they ultimately isolate is this guy. So let's make sure that I did this right. So let's draw this out and make sure we get the right stereochemistry. We have the answer, so we should be able to make sure that we get it right. Right. So we've got our carbonyl. Now what's nice is I can just cheat and turn basically all of this stuff, right? So this whole big long thing, all of this doesn't matter. So I can just say, that's the big group. So you don't have to keep drawing that over and over and over again. So again, if I gave you an example, like on an exam where I was like, okay, draw the Falcon-On model, you wouldn't have to draw this whole thing if you just clearly like said, hey, all of this I'm just going to call L or whatever, because I don't need to draw the whole thing. All that stereochemistry doesn't matter. That's fine, right? It just saves you a lot of time. So, right, we know that we're going to do our oxygen, our hydrogen, circle, right? And we've got to set our stereochemistry, right, to make sure we draw the right stereochemistry. So we're going to be 1, 2, 3, 4. Looks are, hydrogen points at us, it says. Okay. So now, again, I already have the answer, but we'll draw the right one. See, so L, so that's our bigger group. Hydrogen's here, methyl. 1, 2, 3. Again, if we kind of look down at it, right, we go 1, 2, 3. So it's counterclockwise, right? Cool. My one person in class is nodding, so I must be doing something right. Right? So it's counterclockwise. So what I have drawn is S, right? So those two match up. And now my nucleophile will come along this path here and add. So that's going to put my OH and my hydrogen here, my nucleophile there, and then methyl, hydrogen, and my big group. So the last thing left to do is we have to get from this to our perspective drawing, right? So then that is going to mean we have to go like this group back here. So we got to set this chiral center here. So then the thing back, and then nucleophile makes 3. I don't know why every time we do this, it ends up being S. I'm not trying. This is not my goal. I swear R comes out of this. I swear R can happen. And then this will be S, so I need to make sure that I see here. Yep. So then when we draw our product, oops, so many, oh, I guess I didn't even bother to draw it up. So if we draw our product, right, we need to have right. Now, when you would draw your product, I'd let you totally cheat on drawing the thing, like the model, without having to draw the whole thing out. But when you drew your product, I want you to actually draw the whole product, right? So then this would be 1, 2, 3. Hydrogen points at us. It's 4. So looks R is S. So I did it. It's S, just like it's supposed to be. Now, I didn't set this stereo center, right? They do in the actual example, and that's another layer. That's like later in the slides when we get to it, we get to it. If we don't, we don't. But yeah, that stereo center does get set, but it's not for us to worry about right now. One of the reasons I picked this example is I thought it was neat that, draw it out, or draw it so you can see it better, right? So you have or you end up with an aluminum diethyl aluminum on the oxygen. And if you count 1, 2, 3, 4, 5, 6, this actually will close to make a lactone. So they start out with this acyclic thing, and they end up with, did I totally shortcut that there and didn't do tetrahydrogenate and close? I did, but be fine, right? You end up making a lactone in the end. So this is, I know I said this a while back, that if you make something that's reactive, you make a reactive intermediate, right? You shouldn't waste it. So they were able to do the addition that they wanted to do, right? So they're able to do this addition, and they make an O minus. And so they were able to then say, well, we could just add acid to this really fast and just stop, or we could use a reagent that really binds slightly to my oxygen. But instead, they're like, no, let's use this O minus that we generate, right? O minus aluminum plus. Let's use that O minus to then make our lactone that we need later on. So if you look at the slides, I didn't go through everything, but right. So they're able to take this, and the thing that they get a mixture of, they get 2 products, is the alcohol is pretty much the same, right? So they get the alcohol, they get a little mixture, not too bad, and then they're able to get this oxygen to make this lactone. So, right, these part of what makes these groups, or what separates, okay, words, thinking. Okay. what's determining your selectivity is how strongly your G group wants to be perpendicular, right? So in that list that we had earlier, right here, right? If there's not a huge difference in size between methyl and ethyl or methyl and isopropyl, right? They're different in size, but there's not a huge difference, right? So your selectivity is based on basically how big that difference is, how big the priority for being perpendicular is. So basically, even though this chain is a lot longer, right, this chain right here is a lot longer, basically, it's kind of just, you're putting a methyl versus what effectively is an isopropyl group, right? So there's a lot more stuff going on, but if you were to look at it like this, oops, right, you've got, oh, can't see, sorry. One day. I've only done like 50 lectures. One day I'll figure it out, right? So you've got all this, right? And you're like, whatever. But this is all of this, all this like extra stuff kind of past that methoxy group doesn't matter. So you're basically just doing methyl versus kind of isopropyl, right? And if there's not, if there's, if it's a 5-to-1 ratio of, let's say, isopropyl perpendicular versus methyl, you're going to get a 5-to-1 ratio of your alcohols. If you have methyl versus tert-butyl, and maybe that's a 20-to-1 ratio, you're going to get a 20-to-1 ratio. So the desire of your group to be perpendicular, going back, right? So how much a group wants to be perpendicular is what's going to determine your alcohol stereocenter, right? If there's like a mixture, you're going to get a mixture of products. So on the slide, I drew out both, right? Because you can set it up where, yeah, your L group is perpendicular and you go over this hydrogen, right? Just like we wanted, right? But you can also turn it so now your methyl group is perpendicular and you still go over the hydrogen, but you come from the other side. So what determines your alcohol stereochemistry is just the desire, basically how big the difference between your large group and then your next group, your G group, and then the next largest group is. And if they're close, you get a close mixture. If they're far apart, you get a really big difference. Right, and then here's another one. So they actually do this one all out, right? So again, you get your G group here versus rotating it to the other side, puts the L group and blocks the Burgee-Dundas angle. So we want it like this, and that works out that our G group here is our ester. And then we have hydrogen as our small group and this ring as our big group. And we want to go over the hydrogen, and that gives us this alcohol that you see here. And this is just a reduction, right? You just have H minus as the nucleophile. So I think I am pretty much, I guess I have a few more things before I pack it in. Okay. So another thing that matters, right, is how big your nucleophile is. And this kind of makes sense, right? So if you have the same, right? So let me draw it. So as you increase the size of your nucleophile, you increase your selectivity, right? Because you could get kind of for lack of a better word, like leakage of your stereochemistry. So let's say you've got your Falconon model, you've got your G group here, you've got your H, your smaller group, and then you have your larger group, right? You could have this, or right, your G group could flip, right? You could rotate around, and you could put your G on the other side, have large and H, right? So the thing that matters, what's kind of holding this together, is the fact that the G group must be perpendicular, right? And then what's giving this selectivity is that your nucleophile wants to go over the smallest thing, right? So G, perpendicular, and then nucleophile goes over the smallest thing. But G can be perpendicular on either side, right? So if the G flips, if your nucleophile is really small, it could just go over that large group, right, and still approach along the Burgee-Dunlop angle. If your group is big, if your nucleophile is big, it gets pushed away. It doesn't want to go along that path. So the example we have here in the notes, right, is, right, if you have ethyl, right, if you add ethyl minus, right, you get, oh, oops, sorry, thank you for yelling at me. I didn't look over my shoulder. There we go. So much stuff happened since you last saw me doing anything. I will finish drawing and then let you catch up. Right. And then I'm just gonna say, oh, no, ethyl. So the nucleophile wants to go over the small group because the small group's the easiest group to get by. But if your nucleophile is small, it's not really hindered by going over a larger group. So when you add ethyl, right, ethyl's pretty small, you get like an 80-20 mixture of these two products. Right, pretty good selectivity, 4-1. But if you make your nucleophile bigger, so if you have a big nucleophile, it's not going to go over the large group. So if you rotate around and you put that G group perpendicular on the other side, right? If your nucleophile is big enough, the large group effectively will block approach from that face. So it'll only kind of approach from this side where the small group is along the Burgee-Dunlop angle. So when they switched it to tert-butyl, right? So with ethyl, it was 80-20. When they used tert-butyl, they got, what are the numbers here? 98-2, right? So even when the G group was like, I can be perpendicular on the other side, the tert-butyl was too big to go past the large group. So you're picking, your molecule is going into one of two conformations, which puts the G group perpendicular. So you know you're in one of these two conformations. The one that you prefer to add over, or to add to, is one where you go over the small group. But because you have both of these conformations, if you're able to go over the large group, you get a mixture. So the bigger your nucleophile gets, the less times you go over the large group, the greater your selectivity is. Right? The same thing is true with whatever group is here. Right? So we've been using aldehydes, but you can also do this with ketones. So the example in the the thing. But so you have your R group here, and again you've got G, L, and then you've got your H, right? Verse. Did I flip these? I flipped them. Sorry, let me fix it. He's so bad at this. He did it again. H, L, G, L, H, G. So you get the same two possible conformations, right? But when R equals H, you get a mixture of products where you have right, I can just show you, but sorry, I'll draw it. This verse right? So when R is H, you get 72 to 28, right? So not a huge difference when you're adding that methyl group, right? Because methyl is kind of basically the second smallest nucleophile you can add, right? Now you make the R group a little bit bigger. You make it an ethyl. So now the R group is helping to kind of block stuff, right? Because you're not going to want to come between the large group and whatever's on the aldehyde or on the ketone, right? Because now this area here, as you go from hydrogen to ethyl, gets really crowded, right? Because now you've got to get past two carbon groups. Where if you approach along this path, which is what we want, you only have to go past one group, and then the selectivity improves to 80. Was it 86 to 14? So it gets a little bit better. Now, if you go to tert-butyl, right, kind of our default biggest group, right, now you get 96 to 4, because as you get bigger, right, so the bigger R gets, the more crowded this conformation gets, and the harder it is to get to the carbonyl carbon. Where here, on this side, you still got this hydrogen that is easy to get past. So as you make your ketone bigger, you're reinforcing the fact that you need to go over the small group to get to the carbonyl. So now with that, we are literally at the end of class. So I'll try to come up with some examples. We might do a few more new things, but yeah. Like I said, I'm going to work on getting your exam up on Sunday or Monday, and then just giving you all week to do it. So hopefully that's enough time. So with that, I will see you guys, well, half of you on Wednesday, and the other half then all of you on Thursday.